In our last video, we took a look at limiting reagents, and we said that in ideal situations, you have the perfect amount of every reagent to make a set of products. However, in reality, chances are you have more of some reagents than others. Therefore, we need to identify the limiting reagent. So we went through the example with trucks, and then we also did this example with the space shuttle, looking at the limiting amount of oxygen versus hydrogen. And in this example, we calculated out the maximum amount of water that could be made for each of the individual starting materials. And then down here, we said that the one that makes less must be our theoretical yield, which is the same as the maximum you can make. So we're going to actually extend on this today, and we're going to talk about reaction yields. And luckily, this isn't too bad as long as you've got the last part down. So the percent yield for a reaction is going to be your actual yield, meaning what you find as your mass in real life, versus your theoretical yield times 100%. And like I said, this theoretical yield right here is based on your limiting reagent. That's what we just did in our last video. And then up here, this actual yield is what you measure in lab. So this is a real world situation, not a calculated situation on the top there. All right, so then the question is, well, why would our actual yield, meaning what we measure in lab, ever differ from our theoretical yield? What's causing this discrepancy? And really what this is due to are side reactions. So side reactions often occur. And these lower the actual yield. So in the example of the space shuttle, maybe we lost some hydrogen due to venting. Maybe there was incomplete combination. Maybe at one point we were delivering too much hydrogen and it couldn't react fully with the oxygen. Things like that mean that in reality, no reaction gives exactly 100%. We can get really, really close, but most reactions are going to be below 100% yield. So this lowers the actual yield of your desired product. All right, and that's one important part of being a chemist, is trying to identify inefficiencies in your reaction. That way you can improve upon them later. All right, so let's take an example situation, and this will just be more practice. So in this example, it says 5.074 grams of chlorine gas, which is Cl2, is reacted with excess methane. All right, so this immediately gives us a clue, right? The fact that we're saying excess methane means that this is limiting, right? So that's one clue in this problem. All right, the second part of this question says the chemist isolated their product and they isolated 2.745 grams of their product, which is CH3Cl. What is the percent yield? Okay, so let's first write out the actual chemical reaction. So it says that we're going to react chlorine gas with methane, and we're going to get this product out. And the byproduct in this reaction is actually hydrochloric acid, which is HCl. this product that we're making right here is called chloromethane. It's a reagent that's occasionally used in organic chemistry labs. We're really not going to get into the uses of this, but it's really bad for the environment. It's not something we should be using much of anymore. All right, but anyways, we first want to make sure that everything's balanced. So over here, I've got two chlorines. I've got two chlorines on the right, so chlorines are okay. Then next, I'd say one carbon. Those look okay. And then hydrogen, I've got 4 hydrogens, and then 3 plus 1 is 4 over here, so my hydrogens are okay. So it does look like everything's balanced, and it's in a 1-to-1-to-1 ratio if we don't need to include those ones. And then I'm just going to help us with the molar weights here. So 1 mole of this is equal to 70.90 grams. And we'd say 1 mole of this is equal to 16.04 grams. And then 1 mole of chloromethane is equal to 50.48 grams. And then over here, we've got HCl, which 1 mole is equal to 36.46 grams. All right, so we've got the appropriate conversions there. We've got our reaction coefficients. We should be set to go. So let's first calculate our theoretical yield. And like I said, the theoretical yield is always based on the limiting reagent. Okay, so let's consider the chlorine as our limiting reagent. That's the clue we already had. And we said that we reacted 5.074 grams of chlorine. Now let's get rid of the grams unit, put that on the bottom. And we can go to moles. So I'm going to put moles of chlorine on top. And then over here, we said that, well, 1 mole of chlorine is 70.90 grams. So I'll put the 70.90 with the grams unit. I'll put the 1 with the mole unit. So now we've got that taken care of. We've canceled out our grams of chlorine. Now we've got moles of chlorine. And we can tell that if we put in 1 mole of chlorine, we should get 1 mole of our desired product. So let's use that ratio and cancel out our moles of chlorine. So moles of chlorine will be on the bottom. Moles of our desired product, which is CH3Cl, be on top. And it's just a 1-to-1 ratio. I know it seems silly to include it, but it helps us to ensure that we're canceling out units appropriately. Okay, now we're done with that. Now we need to cancel out moles and get to grams. So I'm going to cancel out moles by putting it on the bottom. So CH3Cl, I'll put that on the bottom, that way it cancels. And we want to figure out the mass that we get in grams. So I'll put that on top. And up here, we can see the mole to gram ratio for that. So there's 50.48 grams for every 1 mole. So I'll do let me change the colors back. 50, let me erase this. 50.48 grams on top for every 1 mole. Okay, now we've canceled out moles of our desired product, and we're going to be left with our grams of product. And if you go ahead and you crunch this in your calculator, you should get a value out, which is 3.613 grams of chloromethane. And this, we said, is our theoretical yield. Okay, but that's not what the question is asking. The question isn't asking what's the theoretical yield. The question is asking what is the percent yield. Okay, so let's do that part now. And we could say, well, the percent yield is equal to the actual yield divided by the theoretical yield times 100. So what was the actual yield? Let's go check. Up here it says the chemist isolated 2.745 grams. Okay, so let's put that in the top. So 2.745 grams was actually isolated. However, up here we said, in theory, this would be the maximum amount we could have gotten out of this reaction. So we'll put that on bottom, 3.613 grams. And we'll multiply this by 100. And if you do this, you still want to follow sig fig rules. So we should have 4 sig figs. We get 75.98%. This would be the percent yield for this reaction, meaning the efficiency was pretty good. We got 75% of our maximum yield actually made, but it means about 24% of it was lost due to side reactions or errors in the reaction. But that's just the nature of being a chemist working in the real world. All right, I hope that makes sense, but let me know if you have any questions.